Hello everyone. Welcome to another episode of Deep Dive Knowledge. What are the main challenges in the design of polymer electrolytes for next-generation batteries?
The main challenges in the design of polymer electrolytes for next-generation batteries are the low ionic conductivity of the materials and the vast polymer space that poses significant challenges. For screening and design, the low ionic conductivity of polymer electrolytes hinders their commercialization, while solid polymer electrolytes offer superior safety performance, enhanced specific energy, and longer lifespans compared to liquid electrolytes. Their low ionic conductivity limits their overall performance. Higher ionic conductivity is crucial for efficient ion transport within the electrolyte, which is essential for the operation and performance of batteries. The vast polymer space presents another challenge in the design of polymer electrolytes. With a wide range of polymer materials available, finding the optimal material with the desired properties becomes a complex and time-consuming task. The screening and design process require a comprehensive understanding of the structure property, relationships of polymers and their interaction with ions. These challenges necessitate the development of new approaches and methodologies to overcome the limitations and design polymer electrolytes with improved conductivity and performance. The use of computational techniques, such as GPT-based and diffusion-based generative models, offers a promising solution to tackle these challenges and accelerate the discovery of next-generation battery materials.
How did the researchers in this study address the challenges of designing polymer electrolytes? Using generative artificial intelligence (AI) models.
In this study, the researchers addressed the challenges of designing polymer electrolytes using generative artificial intelligence (AI) models through a comprehensive and systematic approach. They compared different deep learning architectures, including GPT-based and diffusion-based models, to optimize the generation of polymer electrolytes. The researchers also performed hyperparameter tuning to benchmark the results, to assess the performance of different generative model architectures and validate the top candidates. The researchers employed various evaluation metrics and conducted full atom molecular dynamics (MD) simulations. This allowed them to evaluate the ionic conductivity of the generated polymers and compare them to existing polymers in their database. The researchers utilized a closed-loop framework that included conditional generation of polymers, preliminary screening via GNN predictions, evaluation through MD simulations, and data augmentation incorporating new findings. This iterative process enabled them to refine and improve the generative models based on the feedback obtained from the MD simulations. By adopting a pretraining and fine-tuning methodology, the researchers significantly improved the efficacy of their generative models and achieved quicker convergence. They discovered 17 polymers out of 45 candidates that exhibited superior ionic conductivity compared to any other polymers in their database, with some of them doubling the conductivity value. Overall, the researchers combined the power of generative AI models, evaluation metrics, and MD simulations to overcome the challenges of designing polymer electrolytes. Their approach allowed for the discovery of promising polymer electrolyte candidates and paves the way for the development of a self-driving laboratory.
What were the results of the study in terms of discovering polymer electrolytes with improved ionic conductivity? Did the researchers find any candidates that outperformed existing polymers in their database?
Yes. The study aimed to design polymer electrolytes with improved ionic conductivity. The researchers used a combination of generative pre-trained transformers, GPT-based and diffusion-based generative models to screen and design new polymer electrolytes. They focused on optimizing the polymer structure to enhance the ionic conductivity. According to the report, the study successfully identified several polymer electrolytes with improved ionic conductivity that outperformed existing polymers in their database. These newly designed polymer electrolytes showed higher conductivity, which is crucial for the commercialization of solid polymer electrolytes in next-generation batteries. By using the GPT and diffusion models, the researchers were able to explore a vast polymer space and narrow down the search to specific polymer structures that exhibited enhanced ionic conductivity. This approach allowed them to discover novel polymer electrolytes with improved performance compared to the existing polymers in their database. It is important to note that the study provided a systematic and effective method for designing polymer electrolytes with higher ionic conductivity. The use of generative models and computational screening approaches can significantly accelerate the discovery and optimization process of new polymer materials for various applications, including solid-state batteries.
How did the researchers improve the efficacy of their generative models by adopting a pre-training and fine-tuning methodology? How did this approach lead to quicker convergence and enhanced performance with limited data?
The researchers improved the efficacy of their generative models by adopting a pre-training and fine-tuning methodology. This approach involves two steps. First, the models are pre-trained on two different datasets, PI1M and HTPMD. Pre-training refers to training the models on a large dataset to learn general patterns and features of the data. In this case, the models are pre-trained on different datasets to capture a wide range of features and improve their understanding of polymer structures. Second, the pre-trained models are fine-tuned on a smaller dataset specific to the target application. Fine-tuning involves training the models on a smaller dataset that is more relevant to the specific task at hand. In this case, the models are fine-tuned on a dataset of high-throughput polymer molecular dynamics (HTPMD) data. This pre-training and fine-tuning methodology leads to quicker convergence and enhanced performance with limited data for several reasons. 1. Transfer learning. By pre-trained on a large and diverse dataset, the models gain a general understanding of polymer structures. This knowledge can then be transferred and fine-tuned on a smaller dataset specific to the target application. This transfer learning allows the models to start from a better initialization point and requires less training on the target dataset, leading to quicker convergence. 2. Capturing general patterns. Pre-training on a diverse dataset helps the models capture general patterns and features of polymer structures. This increases their ability to generate valid and unique polymer designs. Fine-tuning on a smaller dataset then allows the models to learn more specific details and characteristics of the target application. 3. Leveraging existing knowledge. The pre-trained models already have some knowledge about polymer structures, which can be leveraged during fine-tuning. This reduces the amount of data required for training and improves the model's performance even with limited data. Overall, the pre-training and fine-tuning methodology improves the efficacy of the generative models by leveraging transfer learning, capturing general patterns, and enhancing the model's ability to generate valid and unique polymer designs. This approach also leads to quicker convergence and enhanced performance, even when there is limited data available for training.
How did the researchers evaluate the performance of the generative model architectures and validate the top candidates for polymer electrolytes? How did they use evaluation metrics and molecular dynamics simulations in this process?
The researchers assessed the performance of the generative model architectures and validated the top candidates for polymer electrolytes by employing various evaluation metrics and full atom molecular dynamics simulations, to evaluate the performance of different generative model architectures. The researchers compared the results of deep learning architectures, including GPT-based and diffusion-based models. They conducted a grid search of hyperparameters tuning to compare the average performances of the models. The researchers also compared the performances of different models in each evaluation metric to validate the top candidates for polymer electrolytes. The researchers incorporated full atom molecular dynamics simulations. They used these simulations to assess the properties and behaviors of the generated polymers. This allowed them to determine the efficacy and suitability of the candidates in terms of desired properties, such as high ionic conductivity. In addition to molecular dynamics simulations, the researchers used evaluation metrics to further assess the performance of the generative model architectures. These metrics help quantify and compare the performance of the models in terms of their ability to generate polymers with desired properties. The researchers listed detailed scores of all metrics in Table S1, which provided a comprehensive overview of the performance of each model. By combining evaluation metrics and molecular dynamics simulations, the researchers were able to comprehensively evaluate the performance of the generative model architectures and validate the top candidates for polymer electrolytes. This approach allowed them to identify 17 polymers that achieved superior ionic conductivity compared to any other polymers in the database, with some of them even doubling the conductivity value.
How does the proposed method of using generative AI models facilitate the generation of novel, diverse, and valid polymers for the design of polymer electrolytes? How does it enable the identification of promising candidates with improved efficiency?
The use of generative artificial intelligence (AI) models plays a crucial role in facilitating the generation of novel, diverse, and valid polymers for the design of polymer electrolytes. These models enable the identification of promising candidates with improved efficiency by leveraging their ability to learn the language of polymers and generate chemically valid and synthesizable structures. In our study, we compared different deep learning architectures, including both GPT-based and diffusion-based models, to optimize the generation of polymer electrolytes. These generative models were trained on a curated dataset consisting of 6,024 different amorphous polymer electrolytes with their ion transport properties computed from molecular dynamics (MD) simulations. The generative models can be utilized for both unconditional generation, where the model produces novel and unique polymer structures, and conditional generation, where the model is steered towards generating candidates with specific properties, such as high ionic conductivity. By employing advanced generative models, we can explore the vast polymer space and identify polymers that exhibit superior properties. To validate the performance of the generative models, we employed evaluation metrics and conducted full atom MD simulations. The MD simulations serve as a validation tool, allowing us to assess the performance of the generated polymers and compare them to known polymer electrolytes in our database. Through this closed-loop framework, which includes conditional generation, preliminary screening via graph neural network, GNN, predictions, evaluation through MD simulations, and data augmentation, we can iteratively improve the generative models and identify promising polymer electrolyte candidates. The use of these generative AI models enables us to screen a large number of candidates efficiently and identify polymers with improved properties, such as superior ionic conductivity. In our study, out of only 45 candidates being tested, we discovered 17 polymers that achieved superior ionic conductivity compared to any other polymers in our database. with some of them even doubling the conductivity value. This highlights the effectiveness of using generative AI models in facilitating the design of polymer electrolytes and identifying promising candidates with improved efficiency.
What are the potential implications and applications of the findings from this study in the field of polymer electrolytes and next-generation batteries? How can the discovery of novel polymer electrolytes with improved ionic conductivity contribute to the advancement of battery technologies?